Hello everyone, and Sahaf.com. I hope you're doing well and in the best of your health. So always with the session of JAX for deep learning, and this time we will move to building some models. Okay, so before digging into the session, you're always with Leila Habib, the GDG CD Abbas leader and WTM ambassador. So today's session typically will be about coding, how we can train neural network using JAX, using Flax. So all the previous ecosystem that we saw in the previous sessions. So before moving to the collab, just let me give you like an overview about how we can do or what is JAX and how we can do those things or how we can build neural network using JAX. So as we said, JAX is just like NumPy on a GPU. So it helps us to do some automated differentiation, some, let's say, some numerical computations on on all devices, CPUs, GPUs, and TPUs. Fine. So here it's not, we can't say that it's a mathematical library, but it's also help us to build some neural networks. And to build those neural network, of course, JAX here provided an entire ecosystem that helps to do those specific things. Okay, so JAX alone is not that good definition to build the neural network. So the ecosystem that was built on top of JAX helped to build those models. And in the previous episode, we talked about the variety of the ecosystems that help us to do those specific things. So here, JAX is a NumPy on GPU. We have this HiQ here. You just like have to build neural networks. And the syntax, it's a little bit, it's kind of similar to the context, to the syntax, I mean, of the TensorFlow. So those who are familiar how to build neural networks using TensorFlow, so the HiQ here will be a good fit, and this will be, let's say, an easy approach to do things there. Okay. And here, OpTags, as its name refers, just like an optimizations, it helps us to do some optimizations and building some calling loss functions. And here you may be wondering what are the famous optimizers, or what are the loss functions that we can use here in JAX. So what I want to say, just like exactly the famous optimizers that we know. Okay, so for sure, if you are deep learning developer, so for sure you know some stochastic gradient descent, the Adam optimizer, and so on. So all those famous optimizers, we can call them here with OpTags in a very easy way. And same thing for loss functions. So all the famous or the most used loss functions are available here under this OpTags ecosystem. And I repeat, all those libraries here are built on top of JAX. Okay, so the basic of all those libraries is JAX. And here we have the RLAX here just for the reinforcement learning. We have the NumPy, just like the similar NumPy, the normal NumPy that we all know. Of course, here I'm talking to the deep learning developer. So here the NumPy that we use to do some math with it. So it's just like the same, but it's built on top of JAX. So here we're importing the NumPy from JAX. So this is the NumPy of JAX, and we have also the Flax. So Flax, it's kind of similar to the HiQ. Both of them have to build those neural network. Okay, so here Flax and HiQ both have to build neural network because JAX alone is not that efficient. It's not enough. So we need to seek for another ecosystem that has to do that. So you have the choice: either you use this HiQ or you use Flax, or you can mix everything all together. Fine. So in today's session, we will try to build something or to do something using JAX, Flax, and the OpTags. Okay, so we'll try to use those three things. Of course, here JAX in general to do the computations in general, and we have the OpTags to call the loss functions and the optimizer, and Flax here to build the neural network. Okay, to design the neural network there. Just like it's similar to what we did in TensorFlow, but this time we just like using the JAX. Okay, so the thing that you should do before building neural networks in JAX is just like you have to get familiar with how we can use JAX and how we can call some functions from JAX, even though the majority of the functions that you will see that you are already familiar with them. So just like you should learn how to write them in syntax, in terms of syntax, everything else is exactly like we used to do previously. Okay, so here, just like this is some things. If you are interested about the ecosystem, or if you let's say if you missed this session of the JAX ecosystem, so you can find the explanation in the playlist that will be provided in the private chat. Okay, so today's session is to talk about building models. We have just like building models, as you know, to build models, we should to design that model and train this deep learning on specific data sets. So that's what we will do together in this session, but starting with the MNIST data set. So MNIST data set is just like the hello world for for learning anything. So if you want to learn anything in deep learning or anything like using data, of course, the MNIST data set should be a good fit. Sorry. Okay, so the MNIST data set is a very good fit for you to learn things, especially that the data is clear, easy, and let's say you are already familiar with it. So for sure you did that. You did the MNIST data set when you start learning, let's say, neural network in the beginning or at your first. Fine. So here in this session, inshallah, we will try to go with the MNIST data set. So the MNIST data set is just like the writing digit data set. So if I write here the MNIST, okay, so here if I go to the images, so you can see here, this is my data set. So those are here the MNIST data set. It's just like to recognize the handwriting digits. So we will try to use this data set to build a neural network that will be able to recognize those handwriting digits there. Okay, so I already prepared the code, so we just like go deeper in this code and try to explain it. So for the first thing, we should import the needed library or the libraries that are necessary for our project or to build this model. We'll need JAX, of course, okay, because here we're trying to train this neural network using JAX. So we need JAX, flags. We're importing NumPy here and JAX for NumPy. Okay, you may be wondering what's the difference between the NumPy and JAX for NumPy. So here, this NumPy, it's a very large library. So there are some functionalities or some things in NumPy that didn't exist in JAX. So here we will try to use both. But JAX for NumPy, just like when we import the NumPy here from JAX, just like we're doing NumPy, and we can do them on GPU, because the main thing that we calling JAX here is to accelerate our execution, so we can use it in GPUs, on using GPUs with the same code that we're having. So we're trying to build all the libraries that seem to be that we need it in our code there. Okay, so here we're having the pandas, the OS here, and also we're having here importing Linen from Flax. Okay, so this is Linen is an API, or let's call it a high-level neural network library that provides a simple and an efficient way to build and train neural networks. Okay, it's helped us to build here neural networks, and that you can see here, we're importing it as a neural network, and here to just like to say NN, to say neural network. And of course, it's a build on top of JAX library, which provide a high performance numerical computations. So this Linen API here is used for a variety of tasks, but the main thing, or let's say it's include the building neural networks, because it's provide a variety of building blocks for neural network, including layers, because when we talk about neural network here, which especially we should talk about layers, activation functions, loss functions, and so on. And also we can use it to train the neural network, because this library here provide also a variety of training algorithms that help us to train neural network. And here we can mention the let's say it's include the stochastic gradient descent, the ADAM, the ADA grade, and so on. Okay, so it's It's help for both building the neural network and training the neural network. And also we can add to evaluate the neural network, okay, because it also provide a variety of evaluation metric. And when you talk about evaluation metrics, so here we're talking about the accuracy, the precision, the recall. So all those things are included in this linear library. So it's very efficient. It's really helped us to build those neural network here. Okay, so here in general, this Linen API is a powerful and a flexible tool for building and training neural networks, and it's easy to learn and use since, let's say, it contains similar thing that we used to do in neural network when you start neural network, because of course I believe that you didn't jump directly to JAX, you passed through some deep learning. I don't know, deep learning from scratch or using some frameworks such as the TensorFlow. So here, this linear here, just like pretty much similar to those previous frameworks that we worked with previously, and that's what make it easier, let's say easy to learn, and it's help us to build neural network using this neural in a very efficient and a very efficient way. Okay, so it's really provide a very high performance in task in doing things there. Okay, so here we're importing the Flax training, and we have also the OpTax. So OpTax, as I mentioned, it will be used to do how we say it, the OpTax there is to for the optimizers, okay, to call the optimizers, and the matplotlib in case we want to plot anything there. Okay, fine. So now moving to, this is just like a command to test this JAX dot local devices. Here it's a function that returns a list of all available devices in the current process. So here in this case, we're having CPU device. Okay, so here my code was running on CPU only. So it's just like telling me that the only one device available is CPU, and here it's specifying the ID with ID equal to 0. Okay, so if we want, or if you want to add, let's say another GPU, or if you want to add anything as here, so this function here will list all the available GPUs devices here. Let's say if you are using 2 GPUs, so it just like it may mention or it may list 2 GPUs here with different ID. For example, ID equal to 0 and the other ID equal to 1, and so on. Okay, so far we're not using anything. And here we're just like importing the MNIST datasets, because we will try to build the neural network using this MNIST dataset. And if you're not familiar with Kaggle, by the way, here I'm using Kaggle. Kaggle is a platform that allow me to execute or to run some code exactly like Colab. Okay, what's great about Kaggle is that you can find some other competitions, different data sets, and many things. So here you can simply type the name of the data set that you want to work with it. Okay, in our case, we choose the MNIST. So you call the MNIST, you can find the fashion MNIST, the sign language MNIST, and so on. So I already imported, and you click here, add this data set to your list. So I'm having here this MNIST in CSV file. So we can just like, and this is input. Okay, so you can find that this is the input. We can simply call this MNIST data set from its path, which is input, and here digit recognition. And of course, this inside this digit recognition, we should have the train and test. So this simple submission is for the challenges. Here we're not having any challenge, so you can just like get rid of this simple submissions. What we need here is just like the train and the test data set. Okay, so we're saving the test data set in this MNIST train using this path here. And then we will just like try to make, let's say, to separate the label from the features there. So we created a function here. Where am I? So we created a variable called label. So this label here, we just recuperated label from the MNIST train, because here in the MNIST train, we're having a couple of images, and those images contain label to say, so those are my images. The image, they represent some words. Okay, I just like on the big picture. Okay, so we're having those handwriting digits. So what I supposed to find in my AMNIS data set, those images of handwriting digits, let's say 0, 1, 2, 3, 4, 5, and so on, and the label saying that this drawing here refer to 0, this drawing here or this handwriting refer to 1. Sorry, I'm back. So here, just like when we talk about labels, is when we're having the explanation of each digit what represent, or each handwriting digit and what it represents. Okay, so here we're just like trying to separate those labels from the images that we're having. So my features is the images, and the label is the label when we say 0, 1, 2, 3, 4. Okay, so basically we're having 10 classes here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're having 10 classes, 10 classes here, so I'm expecting to have 10 different labels, and I'm saving them in this label variable here. And then we drop the label from my MNIST train, from this variable of the MNIST train. I drop it. Why? Just like to simply get one variable contain the handwriting digit, and one variable contains labels only. Okay. So here we're having a separated we just like separated the labels from features. So here we're having only features, which are my images. Okay, because we drop label. Fine. I suppose that first of all, we had CSV file. This CSV file contained the image and the label. We saved the label only in a variable called labels, and then we try to save the rest of dropping all my CSV from my CSV file, the label. Okay, so here I'm having label saved separately, and I'm having the features also saved separately. And then here we're having some normalizations, because it's let's say grayscale images. So they are basically some digit, not, let's not call them digits, but they are, when we talk about the grayscale images, they are numbers between 0 and 255. Okay, it's referred to the black and white. So the highest number here is 255. So we try to do this simple normalizations to get a normalized number, and like that my model will deal better. Okay, it's because always I said that, I love saying that, the models love to deal with some small numbers. And here we can see that we're trying to reshape these features, because everything is saved here in this variable called features. So here we're trying to reshape this feature using function called values.reshape, and then we're having here -1, 28, 28, and 1. Okay, so this line of code here of reshape, just like try to reshape my data, or reshape the features into 4-dimensional NumPy array. Okay, so here the first dimensions refer to the let's say the batch size, which is here set to -1. Okay, so the -1 in the batch size tell NumPy to automatically determine the batch size based on the number of elements in the array. So if I have 60,000 image in my list, or in my data, so I get here 60,000. If I have 100, I get here 100. Okay, so automatically it just like it determines the batch, or it affects the batch size to the number of the elements in the array. Okay, and then, and this is useful when the batch size is not known in the advance. Okay, so for example, you don't know how many exactly we're having there, so you simply click write -1, and and it will be restricted number of elements there. Okay, so let's say the example when trying to train a neural network with a variable size of a data set. Okay, so the data set, the variable of the data set will vary from one iteration to the other one. So we're just like simply by specifying it to the -1. So here we're having the let's say the features there, having the batch size of a number of elements there. Okay, and then we transform because this is NumPy. This is where the return in NumPy. Okay, so here we didn't talk about the second and the third element. So we're having 28 by 28, which refer to the height and the width of the image respectively. So here this is the width and this is the height. And this last element here is the number of channels. It's set to 1 to say it's grayscale images. So if you go back to the TensorFlow list, okay, in the TensorFlow list, we talk about the colorful images and the grayscale images. And we said when we're having some colors, here the number of channels should be 3 for the RGB. And here, since we're having only one, that means we have only one channel there. Fine, so here we're checking the shape there. We create a dictionary here, as you can see. So if you're wondering why we created the dictionary saying that images refer to features, because in my features there are only images. It's a CSV file, and the CSV file contains images plus label. Okay, so my features, it's always that they are images, and labels, they are the labels. While we are creating this dictionary here, just like to make it easy to access features and labels separately, and also it's help us to update the features and label of the data set, just like by calling this keyword here. And it help also to save and load dataset. If we do not use dictionary to store the features and label of the dataset, then we would have to store them in a separated variable, and this would make it more difficult to access the features and labels, and it would make it more difficult to update the features and labels of this dataset. Okay, so this is the main reason here for using this dictionary that we're having. Moving now to the most important part, which is designing the neural network there. Okay, so here we're just like trying to design our neural network. So this code, basically, as its name refers, we're having CNN here. So it's defined convolution neural network called CNN. It has 2 layers, each with 32, and 64 here filters, and the convolution layer followed by some pooling layers. Okay, so this is the first part. This is the first convolution layer. This convolution layer contain 32 filter and with a kernel or filter of 3 by 3, and then activation function of a ReLU. Oops, sorry. So this is an activation function of a ReLU, and with that we add the pooling layer, which is the max pool that takes the maximum number of a window shape of 2 by 2. Okay, so remember the padding that will flow over all my image. Or let's say when we talk about padding, okay, so here it's not really the padding, but we're talking about the max pooling, and we're having stride of 2 by 2. And then we're having a second convolution layer. Okay, so this time is 64 with a kernel of 3 by 3 there. And also we added the max pooling. So you can see that here we just like have an idea about convolutions from the TensorFlow. And since we're using the Nenon library, remember this is the Nenon library if I go back. So this is Nenon library, we're calling it as neural network. So in this neural network, there are plenty of things, as just like exactly as I mentioned in the beginning of the session. We have some convolution layers. We have some activation function, such as the ReLU here. This is the second activation. This is the second activation function, and the output of the max pooling layer here is flattened using this line here. When we shaping it, it just like to be flattened and fed into this fully connected layer with 256 neurons. So the fully connected layers is followed by another fully connected layers. Of course, we're using this ReLU activation function in between. So this another fully connected layer contain 10 neurons. Okay, why 10 neurons? Because I'm using the handwriting digits, and basically I am having only 10 classes there. That's why I have those 10 here. Okay, and all by the end we're having this softmax activation function because we're having let's say so many classes. Okay, when we're dealing with a lot of classes, so softmax here is just like good things. Another thing I want to mention or to talk about is this at and for the nenon here dot compact. So this decorator, because here we're using this at here, so it's decorator, is used to tell the Flux compiler that the function is a neural network layer. Okay, so the Flux here is knowing, is fully aware that this is a neural network. Okay, and this allows the compiler to optimize the code for performance. So this really help a lot, especially just like to inform this Flux about what we're doing exactly there. And yeah, that's pretty much it. If you're wondering about this call function here, this call method is the main entry point for this class, because we're using class. That's why we should call here. And this method takes an input tensor and returns an output another tensor. Okay, so the output tensor is probability distributed over those 10 classes here. Okay. Moving now to how we create our losses. Okay, so we designed the model, we designed our neural network. Moving now to the loss functions. Before that, just let me check the chat if there are any questions. So please, guys, if you have any queries or any questions about these sessions, please just let me know in chat. Okay. Otherwise, if you don't have any question, just let me continue for those who are watching the record. So we're defining two classes, the cross entropy loss and the compute metric. So if I talk here, this function here taking parameters two arguments, which are the logit and the label. The logit here is a tensor of predicted probabilities, and okay, for predicted probabilities, and the label arguments here is a tensor of ground truth label. Okay, so this function here use the JAX neural network. Okay, especially here the one hot to convert the label tensor into one hot encoded tensor. We try to have by the end some one hot encoded things to optimize things here. So one hot encoded tensor is a tensor where each element is either 0 or 1. The element at index E, let's say a specific index, is 1 if the corresponding label is exactly the same as the element that we're having. So let's say we are in the element I. So the index is 1 if the corresponding label is I exactly, and 0 it's something else at the anything otherwise. Okay, so the function then use this GMP dot sum. Okay, so this function here just like to sum the product of the logit tensor and the one hot encode that we're having. And let's say this is the one hot encoded label that we just like did here previously. And here the other thing that we're doing after summing those two things here, we're trying to calculate the mean using the NumPy in JAX in mean here. Okay, so this function is used to take the mean of the result, because we really need the mean there to calculate the loss functions. So the result of the cross entropy loss function is a scalar value that represents the cross entropy loss between the predicted probabilities and the ground truth labels. Okay, the cross entropy loss is a measure of how well to predict probabilities match the ground truth label. So the lower the cross entropy loss, the better the model is performing. We use the one hat encoded label because it makes it easier to calculate the cross entropy loss. The cross entropy loss is calculated by taking the sum of this negative log likelihood here or having here, and let's say this is for the ground truth labels. So the log likelihood is just like a label, that is probability of the label being correct. So the one hat encode label, it make it easy to calculate for each label there. And second thing, we're having the second function, which is compute metric. So the compute metrics take also two arguments, which are the logit and the label also. Okay, so the logit argument is a tensor of predicted probabilities, and the label argument here is a tensor of the ground truth label. So the function here first calculate the cross entropy, or let's say the cross entropy loss between the predicted probabilities and the ground truth labels. So the cross entropy is a measure of how well the predicted probabilities match the ground truth label. The lower of the cross entropy loss, the better the model is performing, because here we're trying to calculate the metric. Okay, so the metric to just like help me to know whether my model is doing great things or not. Okay, so the function then calculate the accuracy. Oh yes, here we're trying to calculate the accuracy. So the accuracy is just like it's a kind of a percentage of prediction that are correct, and the accuracy is calculated by taking the mean number here of the indicator function, which is a function that returns once if the input is true and zero if the input is false. So here in this in our case here, the indicator function is used to check if the predicted label is equal to the ground truth label, because the my model will predict something. Let's say I just like give it a picture of zero with a handwriting digit called zero. So I give it this zero. So the output will be here this compute metric. To compute the metric, we just like try to compare the ground truth thing, which is zero, and what my model predicted, because maybe my model will predict that it's a 5 or it's a 3 or anything else. Okay, so this function here returns the dictionary of metrics. Here, this dictionary here contains both the loss functions and the accuracy. So in general, the compute metrics here is a powerful or a very useful function for evaluating the performance of a machine learning model, and the function can be used to track the progress of the model as it trained, and it can be used to compare the performance of some different models. Okay, so this is about the lost, and here we're moving to the train step. Okay, so this is here we're having this function here also takes two arguments. We're having the state and the batch. So the state argument is a dictionary that contains the parameters of the models, and the batch argument is also a dictionary that contains the training data. So here the function first let's say define this function called +fn. This function takes a single parameters called para, which is a dictionary that contains parameters of the model, and then the function use this CNN function here to apply the model to the batch of images. Okay, we're having a batch of images, or let's call it tensor. So the result of this operation is a tensor of predicted probabilities. So the function then calculate the cross entropy loss between the predicted probabilities batches and the cross entropy loss in the measure of how well the predicted probability match the ground truth label. The lower the cross entropy loss, the better is your model performing. Always, we are seeking to get a lower loss function. We'll try to get the very low loss function. So the lower we're having, the better my model is performing. And then this function here use this value and grade function to calculate the gradient and the loss function with let's say the gradient of this loss function with the respect of the parameters of the model that we're having there. So the value, or the JAX value and grade function, returns a tuple of two values, the value of loss functions and the gradient of the loss function, which respect the parameters of this specific model. The function then here it's using the apply gradient method, and this method here it's have or it's used to update the parameters of the model using the gradient, and that was calculated by this value and grade seen previously. Okay, so the function then uses to compute metric function to calculate the loss and the accuracy of the model on the current batch, and to compute the let's call it the compute metric function here, that will return the dictionary of metrics. So the dictionary contains losses and accuracy. The function then return the updated state of the model and the dictionary of metrics that we're having, because it's return states and metrics as it mentioned then. So in general, this train step function is a very useful function for training machine learning model, because the function can be used a model on a batch. The function can be used to track progress of the model as it's trained, and it can be used to compare performance of a different model. Okay, so that's pretty much it. Here we're having we're just like trying to specify number of or let's say the batch size. Okay, and we're printing here the overall batch size for both for training and for the eval is, and we're having here the total number batch of size calculated by this specific function that we're having here. And then we're having this train epoch. So this function here takes the argument, the state and train dictionary. We have also the batch size and the number of epochs that we're having. So the state argument is a dictionary that contains the parameter of the model, and the train dictionary argument is a dictionary that contains the training data, and the batch size argument contain both dictionary and batch size argument. And the epoch argument here for to specify the current epoch that we're having, because we will loop over it. So the function then generates a random permutation of training data. The random permutation is used to shuffle the training so that the model does not overfit the data. So each of this random permutation, for each permutation, the function try to create a batch of data and call the train step function to train the model on the batch data. So the function then appends the metric from the train step function to a list. The function here then calculate average metric of the epoch, the average metrics, and let's say those metrics here are calculated. Those average metrics here are calculated by taking the mean of the metric from the list there. So the function then prints the how we call it, the epoch number, the loss, and the accuracy. So the function then returns the updated state of the model and the dictionary of the average metric that we're having. Okay, so this is about train epoch. Of course, we will have a couple of epochs that we should have. We will have specific epochs to train our model. The number of epochs will be defined later. Okay, now moving to this create train state. Okay, so here this create train state takes those three arguments. We're having the RNG, the learning rate, and the momentum. So here the first argument is the random number generator key. The learning rate argument is the learning rate, and the momentum argument is the momentum. So the function is first initialize the CNN. Here the CNN is initialized by calling the init method of the CNN class. This init method takes a random number generator key and batch of the data as argument. the batch of data is used to initialize parameters of the convolutional neural network that we created previously. So the function then, it tries to initialize the parameters of the current convolutional network. The parameter of the CNN are initialized by calling the parameters properly of the CNN class. So these parameters return the dictionary of parameters that we're having here. So the function then creates an optimizer. This optimizer is created by calling the stochastic gradient descent by using here this optax here. We're calling this optax from. Okay, so just see that the quality wasn't that good. Sorry. So we're trying to zoom in here. I'm sorry for that. But here we're just as I mentioned, we're trying to use this stochastic gradient descent. Okay, so we're calling this optimizer here from this optax module. So this optimizer take learning rate as parameters and also the momentum as an argument. So the learning rate is the learning rate that will be used by the optimizer, and the momentum is the momentum that we'll use for the optimizers. Okay, so the function then returns a train state. Okay, so here we're having my train state here. The train state is dictionary that contain those key here. We're having all those key here. We're having this apply fn. The apply fn key is the function that will be used to apply the CNN to the batch of data. We have also this params here. It's a key. The key is this key here is a parameter. Or let's say is dictionary of parameters that will be used to apply. And the last thing is this fn, which is key. It's an optimizer that will be used to train the convolutional network. Okay, so those here, and of course, here we just calling this random number and try to initialize this randomness here to find the learning rate and the momentum to calculate the state there using this create state function. Okay, so we can move down here. So we arrive to the last part here. Here in this code here, just like you're having this loop here for 10 epochs. So the for loop here takes those steps here. It creates a random number. Okay, it tries to create a random number generator key for the current epoch, because here it's an inside the loop. So this random here, it's for the current epoch. It's called the train epoch function to train the convolutional network. Okay, we're trying to train on the current epoch. So here when we're training here, we're specifying the epoch. I mean, we're doing this training on this current epoch. Okay, and of course we're having those parameters here, such as the state. So the state of CNN. We're having the train DS, which refer to the training data set. We're having the total batch size, which is the total batch size, and then we're having the epochs here for refer to the current epoch. And also we're having this input energy, which is a random number generator key for the current epoch. Okay. Okay, so I don't know how to solve. Fine. Okay, just trying to zoom by there. Okay, and here we're having, let's say, this train epoch function return an updated state of the current of the recurrent neural network, or not recurrent neural network, but the convolutional neural network, using those gradient and loss functions that we have previously. And here it's it's return dictionary. This dictionary here that contain those matrices that we will be used. Okay, that contain the loss and the accuracy of the convolutional networks. Okay, as you can see here in the output. So if you go back here into the output, so for each epoch we're having both the losses and the accuracy that we're having. Okay, So for the loop here, this for loop that we used will train the convolutional neural network 10 epochs, because we specify the number 10 here, and append the accuracy of the convolutional neural network on each approach to this list. Okay, because we created this list here, and we're trying to using this append here to save those accuracy and losses in my things there. Okay, so this is for the thing that I were having here, and by the output here we got this list of accuracies that we're having here, and also we got the different losses that we're having. Okay, by the way, here I use only CPUs. Of course, you can try to change the accelerator. You can change the accelerated here from here, and you can check it by using the device up there. So yeah, that's pretty much it. That was about the how to train the MNIST dataset using the Flax, OpTax, and JAX in general. Do you have any question, guys? Any question, guys? Okay, so just like to sum up, let's see what we did in all everything. We called the MNIST dataset or the digit recognition function, and then we separated the label from the features here. We designed our neural network. Okay, so here we just like designed the neural network. So I think the screen wasn't zoomed in previously. So here I'm just like zooming to do this recap. Here exactly like TensorFlow, we're just like calling some convolution layers, pooling layer, and we're having my activation function here. And this is my output layer that contains 10 features and listed that way. Okay, so for sure that will remind you about how about the TensorFlow for sure. And this is used, this line here is used for the flatten. Okay, and then we did we let's say we defined our cross entropy for loss, the loss cross entropy, and compute the metrics to calculate the loss functions, and to calculate to compute the metrics. My metrics contain the loss and the accuracy, and of course we specify the end the looping over my data set with a specified number of epochs, and we got this result. Okay, so far let's say it's nice result so far, and of course we can get or we can have better resulting. Okay, any question, guys? Okay, you can wait for a few minutes to check whether you're having a question or not. And also another thing, please guys, if you want to recommend any topics talking about JAX or Flax or OpTax or any other of those libraries, please just let it in comments. Or if you need any topic related to JAX for deep learning, just let me know in comments and we can prepare a session for that. Okay, I'll be checking the comments even after the live. So please, whenever you watch this recall and you feel that you need any session about any specific topic related to JAX in general, okay, JAX and all the ecosystem of JAX, please just mention it in the comments, and I will do my best to prepare a session for that. And now, okay, let's wait one more minute. So here, so far, if I think maybe the next session will be about computer vision with Flax. Okay, we will go in depth to talk deeply about the convolution layers. Okay, of course, if you suggest any other topic, we can change it based on your need. Otherwise, if you don't have any question, thank you so much for attending. Thank you so much for joining us today. And see you in another episode in the next month, inshallah. Salam.